I'm John Gertz, SETI theorist. Today I want to continue with our discussion of the Drake equation with the next factor, F sub L. For Drake, that represented the fraction of Earth-like planets that bear life of any sort. However, since we've included an expansion, or we've discussed an expansion of the notion of N sub E, that is to say, the number of Earth-like planets, to also include the total number of planetary bodies, be they planets, moons, asteroids, Kuiper objects, or comets, or any other object in the solar system that might harbor life. Then FL sub L takes on for us a new meaning. That is to say, it is now the fraction of all stellar systems that might harbor life. Now, strong arguments can be made that life is common in the universe, that biology emerges naturally from chemistry in the same way that chemistry emerges naturally from physics. We don't know that that's the case, but I think there's good reason to suspect that life is, in fact, common in the galaxy. We can base this on a number of sets of reasons. First, there seems to be a great deal of organic chemistry going on inside the galaxy and outside of our own solar system. Interstellar dust and gas clouds and the even denser molecular clouds that make up, for example, the Orion Nebula are replete with organic molecules. Life as we know it is based upon carbon, which forms strong bonds with hydrogen, oxygen, nitrogen, and other atoms. Interstellar molecular clouds condense into these stars. The clouds are filled with carbon, and thus organic chemistry is baked into our star's birth as it is baked into the birth, presumably, of all other stars. So, for example, when the ancient remnants of this star creation, for example, comets and asteroids, crashed on Earth, we discover amino acids. For example, the meteorite that landed in Australia in 1974, which is known as the Murchison meteorite, was recovered almost immediately upon landing and therefore was not contaminated, was found to contain 74 different amino acids, including 8 that appear in terrestrial biology. Another line of evidence is that precursors of life were created in the famous 1952 laboratory experiment performed by Stanley Miller and Harold Urey, where they zapped a beaker that contained the atmosphere that they thought was prevalent on Earth at that time with electricity that would have simulated lightning, and lo and behold, organic chemicals were formed in the base of that. That experiment is, under many conditions, has been repeated over and over again with more or less similar results. More recently, Jan Sadwidnik and his colleagues succeeded in creating fully self-replicating molecules from mixtures of simple chemicals. And crucially, these molecules competed for resources and seemed to evolve in a Darwinian fashion. Although the pathway from very simple organic chemistry to RNA, DNA, and proteins is overwhelmingly daunting, this may not be the case if we look at it in terms of very small individual steps whereby simple replicating but imperfectly replicating molecules compete for raw materials, and where the most efficient molecules differentially self-replicate more often, creating new generations of more efficiently replicating molecules, and on and on and on. This is Darwinian evolution applied to pre-life molecular chemistry. Where there's replication and variation, evolution can take place. If Darwinian evolution began long before the evolving entities could be considered alive by almost any definition, then the spot where life can be defined as such becomes sort of an arbitrarily chosen place on a spectrum of possibilities spanning from inert molecules to self-replicating molecules to information-bearing molecules to microbes and so forth. Another line of evidence, and a compelling one, is that life began on Earth almost from the very instant it was conceivably possible. no later than 700 million years after the formation of the solar system and the Earth, or more particularly, right after what's called the late heavy bombardment of asteroids and comets died down, uh, and the Earth, became at all hospitable for life. For example, the great agglomerations of fossilized microbial colonies known as stromatolites date back to 3.7 billion years ago, while recent analysis of Canadian rocks dated to at least 3.7 billion years, 7.5 billion years ago, and possibly as old as 4.28 billion years ago, show clear evidence of changes wrought by bacteria. Not only did life begin at the first possible moment that it could here on Earth, but it's extraordinarily hardy. Life has been found in the boiling sulfuric acid laced water found in the geysers of Yellowstone. It's been found in Antarctica, in Death Valley, on the uh, high desert plateau of Atacama, Chile, where it's bone dry and exposed to UV light, as well as in rock formations. Life has been found underground. So, although an exact calculation of F sub L may be very far off, I think there are reasons to believe that we're going to know whether it's closer to zero or closer to one, or 100%, within the next few decades, certainly within the lifetimes of some of the younger um, members of the audience of this video, and maybe within my lifetime too. Um, Put simply, if we find even a single microbe of independent origin, of independently developed life, sui generis life, anywhere else in our solar system, or if we find evidence for it in the atmospheres of exoplanets, then it becomes reasonable to conclude that life in the universe may be ubiquitous and that F sub L approximates 100% or 1. If that's the case, it can come right out of the Drake equation, because once something equals 1, it doesn't add any information, as we've discussed before. So if a systematic search within our own solar system finds no example of sui generis life, then the argument for a very low F sub L may be strengthened. Although there's a major caveat to that, and I'll get to that a little bit later. In the meantime, there are quite a number of upcoming bites at the apple, what I'm going to call bites at the apple, where we might be able to find out whether or not there's other life in our own solar system. Mars, of course, is a great big candidate, probably first on everybody's list or close to first. It's been determined without any doubt anymore that and from many lines of evidence that water once flowed on the surface of Mars. We know very well where there's water, there might be life. For example, the Mars Reconnaissance Orbiter has photographed riverbeds, alluvial plains, lake beds, and gullies, and so on. The Mars rover Spirit and Opportunity found clays and hydrated sulfates and salts and opals and other minerals that can only be formed in the presence of water. Most recently, well, let me start by saying that that back in 1976, the twin Viking landers, Viking 1 and 2, tested Martian soil for evidence of microbial life. One of the 4 life detecting experiments registered positive results in both Vikings. After feeding a containerized soil sample of a broth of radioactive nutrients in solution, the air above the contained soil was tested for radioactive byproducts that might suggest that something in the soil was actively metabolizing those nutrients. The air above the soil indeed was radioactive. The Viking labs then sterilized the second batch of soil and reran the test, and as would be expected of the sterilized soil, the results were now negative. However, another experiment tested for actual organic chemistry in the soil, and its results were negative. And although there's great controversy to this day, the preponderance of scientists felt that the that the second experiment trumped the first experiments, and so life was not definitively found there. But it's highly indicative and begs for replication. We all remember that on August 7th, 1996, President Bill Clinton ran breathlessly before the cameras to announce that a Martian meteorite contained microbial Martian life and other with several lines of evidence, including microscopic pictures of purported microbes themselves. A lot of controversy to this day on whether that's true or not. Probably the most exciting evidence came just recently when NASA's Perseverance rover discovered or photographed a rock with what it's called leopard spots that looked very much like microbial activity or fossilized microbial activity. The pictures are not definitive. Those rocks will have to be retrieved and analyzed in Earth-side laboratories to be definitive. But there's enough there to intrigue. The second bite of the apple is in Enceladus. Over 100 geysers were observed by Cassini during its 13-year exploration of Saturn and its moons. The moon is known to possess all the key elements for life as we know it, including carbon, hydrogen, phosphorus, sulfur, nitrogen, and oxygen. Organic molecules were detected in the geysers, along with trace amounts of methane that might be indicative of microbial waste products. We definitely want to send a spacecraft through those geysers, take samples, and for further analysis. We've got other bites. The third bite of the apple, I'd say, are Jupiter's icy moons of Europa, Ganymede, and Callisto. All of them have oceans, and those oceans can be, in the fullness of time, need to be analyzed for possibilities of life. The fourth bite at the apple that we might have is landing a craft on Titan, a moon of Saturn that has liquid hydrocarbon rain, rivers, and lakes. Now that would not be life as we know it, because DNA does very well in water, but it doesn't. It's not able to persist in liquid organic chemicals. The fifth bite of the apple would be the clouds of Venus. New models of Venus speculate that Venus was temperate enough for liquid water to persist on its surface up until about 1.5 billion years ago, at which time massive volcanic eruptions covered the planet in a sea of molten lava and released carbon dioxide into the atmosphere to create the hell-like conditions we see today. But as one ascends up into the clouds of Venus, the temperature and air pressures drop to something that are not dissimilar to the conditions on Earth. And in fact, there has been a discovery of phosphine that was purportedly made in 2020. It's controversial, but there's no known way in which nature can produce phosphine except as a waste product of anaerobic microbes. The atmosphere of Venus has plenty of carbon chemistry and water vapor, but also, as we know it, I should say life as we know it, destroying clouds of sulfuric acid. The sixth bite of the apple, I would say, would be strange life here on Earth. All life that we've examined to date seems to have evolved from a single common ancestor called Luca, the last unified common ancestor. But we really haven't looked deeply enough into all of the life on Earth to know for a fact that all life is derived from the same life. It may be this strange life, a different form of life exists in the depths of the Earth or the depths of the ocean. Simply, we just don't know. Those examinations have not taken place. uh, or definitively taken place. Uh, the seventh bite at the apple, I would say, are exoatmospheres, and we've discussed this in a previous video. Uh, so the James Webb Telescope is the first telescope to really look at exoplanet atmospheres. To some degree, it will be able to do this, but near future telescopes will do a much better job. The eighth bite at the apple, I'm going to say, is SETI, because if the SETI experiment succeeds and we discover intelligent life, well, intelligent life is also life. And so it also, so it would be a positive outcome, obviously. Now there's a wild card here, and that is interstellar panspermia. Interstellar panspermia is the real wild card here. It may be that the Earth was and other planets or moons in our own solar system were infected by interstellar objects early in our solar system history. We know that interstellar asteroids, comets do course through our solar system. The first one that we've observed is Oumuamua, but models indicate that they routinely come through our solar system. If they were infected with life and crashed into our solar system early, they could have infected it. More intriguingly, it may be that life itself is quite rare, but once it does begin on any solar system anywhere in the galaxy, it evolves into intelligent life. And that sort of ET, that early original ET, resolved to remedy the situations of life's rarity by simply, like Johnny Appleseed, sending probes throughout the galaxy, impregnating newly formed planets. So the implications for the Drake equation are kind of enormous. I mean, if again, life would be more or less ubiquitous in that case. However, the fly in the ointment is that if we discover life on Enceladus, and life is the same as life on Earth, DNA-based, RNA-based, it may be because the original ET that infected us with basically the same microbes. What they could have done is just send microbes to each planet that are DNA-based, RNA-based, and have them evolve as they will. You know, and so that effectively we ourselves are ET. Finally, the Drake equation assumes that life is biological, as that term is generally understood, squishy beings with, like ourselves. It doesn't consider that artificially intelligent post-biological beings. It may be that squishy beings invent, in effect, their replacements that are silicon-based and are robotic, and that these might then seed new planets with either biological life or post-biological life. Well, in one way or the other, I think we'll, as I said at the outset, those younger viewers may have some real answers in their lifetime. Maybe I will even have some major answers in my lifetime. Anyway, thanks for listening today. I'm John Gertz, SETI theorist. You can visit my website at johngertz.com, and I hope to see you next time.